In our today's class, we will start with our second chapter, that is Transistor Biasing. Transistor Biasing. Now, the question comes is, what is biasing? Biasing means, what is that? It is application of proper DC voltages across any of the device. Is called as what? Biasing. So, now we will see how to bias a transistor. So, transistor has got three terminals, isn't it? So we have a transistor. So I have shown what this transistor is called as. It is NPN transistor, isn't it? NPN transistor. So it can be of silicon or germanium, isn't it? So it can be of silicon or germanium type. So I have taken silicon transistor. It is an NPN transistor where this arrow mark shows the direction of current, isn't it? This is NPN transistor. For PNP transistor, we will write somewhat like this, isn't it? So this is PNP transistor. So this is PNP transistor. This is NPN transistor. So we have terminals called as, this is collector, this is base, and this is emitter. Isn't it? So we have emitter, base, collector. These are the three terminals of your transistor, isn't it? So we have studied all these things in our previous year, isn't it? So now collector, base, and emitter. Emitter is the terminal which emits the charge carriers, and collector is the terminal which collects the charge carriers, and base is the control terminal, isn't it? So emitter emits the charge carriers, and that has to go through what? Base to collector, as we have these charge carriers. In the sense, here we have NPN. N means what? Majority charge carriers are what? Electrons. As electrons move from emitter to collector, so collector current flows from collector to emitter, isn't it? So current through a transistor is called as what? Collector current IC. Okay, so now current through a transistor is called as what? Collector current IC. And for this thing, so we have a transistor which has got three terminals. So we need at least of two bias voltages, isn't it? So two bias voltages need to be applied. One to your base to emitter terminals, and other to your output side, that is collector to emitter, isn't it? Proper application of your bias voltages across your base to emitter terminal and collector to emitter terminal is very much important to make your transistor to work as you want. Okay, so for this reason, so we need biasing. Application of proper DC voltages is called as what? Biasing. So now we are learning about transistor biasing. So we will see why we need, how we will apply the proper DC voltages across the transistor. And next thing comes is so we need two bias voltages, isn't it? So now next thing comes is need for biasing. In transistor biasing, what is the need for biasing? So this is one of the questions which will be asked, and they also ask about biasing. So what is biasing? For 1 mark they can ask. Okay. So now next is transistor biasing needs. So need for biasing. First need is operating point Now, here are 3 points for need for biasing. Okay, so what is the need for biasing? So we have written 3 important points which comes under need for biasing. So first thing is operating point should be at the center of the active region. So we have learned about active region. Active region in the sense saturation region. So saturation region is very much important. In our previous chapter we have seen the different regions in your characteristics graph, isn't it? So active region in the sense saturation region, wherein the operating point is a point in your transistor characteristics wherein we will be seeing for the performance of that particular device. In your transistor biasing or in your transistor application, so we will see the operating point in the sense, so what is that? It is the point wherein your transistor is getting operated. So that is called as operating point. So your transistor is operated at a point. So that point is called as operating point. So in which region you are operating your transistor, so that point we will specifically mention where your transistor is operating in the characteristic graph. Okay, so that point is called as operating point. So we will call it as operating point, or Q point also we will call it as Q point. We will also call it as Q point. So it is very much important. Okay, so we will come across this many times in this chapter. So operating point should be at the center of the active region. Active region is a saturation region. So operating point should be at the center of the active region. Okay. So then, so why is that needed? Is so when you bias your transistor, we will make your transistor to get ready for operation. Okay. So at that time we are not applying any of the input signals. When you apply input signal, so then again the current and voltages vary. Okay. So at that time the operating point should not shift, or it should not be going to cutoff region, or it should not be going to saturation region. Okay. So that is the point over here. So operating point should be at the center of the active region. Okay. So then next second point is stability of collector current under temperature variations. Okay. So as we know that as current increases or as temperature increases, your current also is going to increase or decrease. Okay. So there and there, isn't it? For your semiconductors, we know that as we increase the temperature, current also increases, isn't it? So what we need is we need stable current. So we want stable output current to be produced by the transistor on the temperature variations also. So we know that like temperature may increase anytime, isn't it? So increase or decrease anytime. At that time the collector current should not vary. So if your collector current is getting varied, so then it is not a good thing, isn't it? So that's why we want stable collector current under temperature variation also. Okay, so we need the collector current or output current to be stable. Okay, so as we know that temperature affects the current. Okay, so that is why what we need is need for biasing. So proper biasing also eliminates the variation of your collector current, isn't it? So stability of collector current is very much important. So second point is stability of collector current against temperature variations. Okay, and third point is what? Operating point should not shift if you replace transistor, or what we have designed a circuit, or I have given proper biasing voltages, isn't it? So then if I replace the transistor by another transistor of the same time, at that time nothing should change. Okay, so this is our third point. Okay, so like that we have 3 of the important points for biasing. Okay, so this is where we need proper biasing, so to make your transistor to work as you require. So these 3 points are very much important, and they will be asking this question for 2 months. Okay, so now this is a transistor biasing need. Next term is So now we will see the characteristics of your transistor characteristics. Okay. That was output characteristics. Output characteristics. Okay, now I have written output characteristics for your transistor. So that is NPN transistor, isn't it? So NPN transistor, and this is your common emitter configuration where we will be seeing this transistor is operated as. So now we will see the different terminologies here. So here in this characteristics graph, so here we can see in the x-axis we can see the variation of your output voltage, isn't it? VCE, voltage across your collector to emitter, that is in volts, and this is your output current, that is IC. IC is what? Your output current, so that is measured in milliamperes. So this is your output voltage versus output current with respect to different input currents. So here base current is your input current. So base current we will make steps of different base currents, isn't it? So if I make IB1, so this is your base current. So then your characteristics graph will be varying accordingly. As I increase VCE, IC also increases in this manner. For this IB1. Fine. So then next, if I set IB or base current to IB2, if I set base current to IB2, so if I vary VCE from 0, likewise, so collector current increases in this manner. Fine. So the next is IB3. If I set base current for IB3, so then collector current increases in this manner on application of your VCE. Okay. So then if I set base current for IB4, so then again collector current varies in this manner on application of your proper output voltage. So what we can make out here is, so base current IB4 is greater than IB3, is greater than IB2, is greater than IB1. So as I increase the base current, the output current or collector current also varies or increases. As I increase the base current, output current, that is collector current, increases. So that is why we call transistor as what? Current control device. Input current input current decides the output current, or input current decides or will make the output current quantity. So how much current, output current we are getting at the output, so it is decided by the input current, that is base current, isn't it? So here base current is your input current, collector current is your output current or current to the transistor. As I increase the base current, the collector current is also getting increased. So on application of your output collector to emitter voltage. Okay. So here we can see different characteristics depending on different base currents, isn't it? So now here we have seen so many things. So here as I come to this very less current, so this region is what is called cutoff region, isn't it? We have seen this thing in our previous chapter, isn't it? So this is your cutoff region, and here comes the active region. So this is what is ohmic region, isn't it? So here comes the active region. Active region in the sense, so it is the region wherein, so we have the collector current which is getting or which is remaining constant almost. So this region is what is called active region from here to here. So it is what is called active region. So your operating point in the sense your transistor, where your transistor is operating. So operating point decides where your transistor is operating, and that thing is decided here. What we want by condition is, so the operating point should be at the center of the active region. This is your active region, or we can say it as what? Saturation region. So in this saturation region, the operating point should be at the center of the active region. So operating point should be somewhere here. Somewhere here it should be. Okay. So we should not go more towards the saturation point. So this is the maximum point. So that is why this one is what? Saturation point. So this is the maximum current what you can expect. Okay. Through your transistor. So that is why we call this as what? This point as what? Saturation point. And here this is the minimum current. So this is what is what? Cutoff point. We call this as what? Cutoff point. So okay, fine. So this is saturation point. This is cutoff point, or the operating point should be at the center of the DC load, or we can say it as what? Active region. Okay. So next thing comes is DC load line. So this is very much important thing. Okay. So DC load line. So what is this? DC load line. Load line in the sense, what is that? It is the output device which is getting the current and voltages, isn't it? So that is your load line. So DC load line. So what we call it as what? So we want a straight line. So we are talking about a straight line. So DC load line. So we are talking about what? we are talking about a straight line, so which decides the characteristics graph, which is found in the characteristics graph and which will say about the transistor. Okay, so now we will see about the DC load line. What is this? So DC load line is nothing but it is a straight line. It is a straight line drawn in the output characteristics of your transistor, which will give us different DC voltages and different DC currents values. Okay, so for different DC voltages, we have different DC current values, isn't it? This is an intersection, isn't it? So if I go for this point, this is an intersection wherein we can see here, wherein we can make out this is your DCE and this is your IC, isn't it? So if I go to this point, so this is your DCE and this is your IC. So for different voltages, for different output voltages, we have different output currents which will be represented. So that is a line. So this is a straight line which will represent different output voltages and different output currents in your output characteristics graph. So this line is called as what? DC load line graph. Okay, so this is called as what? DC load line, which is found in the output graph of your transistor. Okay, so this is very much important. And now what you can make out is operating point. Operating point, sometimes they call it as operating point should be at the center of the active region, and also we will call it as what? The operating point should be at the center of DC load line. This point also we can say in the need for biasing. Okay, so the operating point should be at the center of the load line. We can say in this manner also. So we can say it as it should be at the center of the active region. So that is also correct, and it should be at the center of the DC load line. So it is an imaginary line what you can make out in the output characteristics, which will give us different DC voltages and different DC currents. Okay, so this is how we can make out the characteristics graph. So important things are DC load line and the active region. So that is nothing but your saturation region. This is the region wherein your transistor will be very much active and it can be operated as you want it as. Okay, so amplifier is the best application of your transistor. So transistor when operated in the active region, it is a best amplifier. It gives proper amplification when it is operated in the active region. So it is done for this class. Okay, so in next class we will discuss about different regions or different values of your output and input currents. So that we will see in our next class.